What I am recording now, by the way, and it can hear me. You can see that the green line is going up and down. That means it can hear us. I don't need
Was always money.
the microphone. No, I mean, it might come handy. All right. What we could do is give an example. So what does it mean that prove the sum of two consecutive even numbers is always even? So two consecutive even numbers, give me two. 2 and 4. So we're saying 2 plus 4 equals 6. Done, right?
No.
No.
Proof for every.
Proof for everything. So we've shown that one example works.
Could be only.
That's not a proof. All right. So you go, oh, I'll give you another one if you like. You could give me 500 million examples, and I would still say that's not a proof. Okay. Because there's potentially one out there that will prove you wrong. And that brings us to a different type of proof in a bit, which is proof by contradiction. All right. There's two levels to proof by contradiction. One is proof by counterexample, and then there's a formal proof by contradiction. All right. So we'll look at the counterexample one in a bit, but we're doing deductive proof here. All right. And basically, we're just going to have to form equations and they show what I need them to show. All right. So how do we do it? That is an example. That's not enough. So what we need to do is have a way of writing a general rule for an even number.
A and B.
2x where x is.
Okay. And that's important. If you don't mind, I'm not going to use x. I'm just going to use n, just because that's what you'll end up seeing in mark schemes and things, right? But you are also good to say where n is an integer. And that's part of the proof. Okay? That's a z. Yeah. Z.
Does that mean it?
So yeah, if you think back to your sets, a fancy looking Z like that means integers.
What is integers?
Whole
Whole
numbers.
Whole number. Whole number.
Like
one.
Yeah.
Yeah, that's it.
All right. So we have to state that. If you don't state that, you'll lose a mark in your proof. All right. So 2n is even. Okay. What's the next? The next even number going to be?
2n plus 1.
Plus 2.
Almost. 2n plus 2.
Or do you think?
But then 2.
2
Oh wait, no, 2 and then bracket f plus 1. Oh, man.
Yeah, okay.
I mean,
You could do that as well. All right, but 2n plus 2. All right.
Expand the bracket.
Yeah. So what we're then going to do is we want the sum of two consecutive numbers. So 2n plus 2n plus 2 will equal 4n plus 2. Okay. So what? How do we prove that?
Just divided by 2.
Okay. So the final, and this is what I often have to write little comments on when in exams and stuff. We then write 2 times n, 2n plus 1. Okay. So we can say, therefore, 2 is always a factor,
Of 2 and then 2.
hence the sum is always even. And there is a little thing, I've never done it, but the boys in upper sixth, someone must have told them this, and then they write QED.
What do you mean?
which I did find out the other day in Latin what that meant. You might have to look that up. I can't remember what it was. What does QED? I'll pause. Should have recorded that. So
Maybe
the
you have to say it
statement.
again.
I should, shouldn't I? The statement means you are finished. You can write QED or you cannot write QED. It doesn't matter. But you have to write. Therefore, 2 is always a factor. Hence, the sum is always even. Right? In a proof question, there is formality to the question.
What type of proof is this?
So this is deductive. So you are deducing, okay, something. Right.
Like,
So I will say that. So certain things for you to remember. Even number. 2n. Okay. How do I express an odd number? 2n plus 1. Yeah. This one's an interesting one. Any number can be expressed as
and
10n plus k.
why?
Why not just n plus one?
Why not just n?
Why not just n? So, for instance, if I wanted to express 31,
N is 3.
well, n is
Three.
3,
Chose one.
k is 1.
Yeah.
All right. Now, you might go, what's the point? But when you need to break numbers up into things, all right, so what would be the next number?
32.
So
But in a general term, if I was going to use it in a proof, it
10
would be
plus
10n plus k
plus 1.
plus 1, right? So having a way to express, so we've got a way to express all odd numbers and all even numbers, but having a way to express every single number, right? On any real number, we should kind of say as well, yeah.
when you get to like 100, would you do like 10? Would you do like
10
100?
times 10?
Would you do like 100 a different letter and then 10 and then?
No, so every number can be expressed. Because
Yeah.
the reason why it's a 10, I don't know whether you've picked up on this. What base is our
Yeah.
number system?
10.
Base 10. So we count up in tens.
Yeah,
If I wanted a different base, let's say I wanted base 3, every number could be expressed as 3n plus k. Right?
Like
So if I wanted the number 100, n is just 10. If I wanted the number 1,000, n is 100. Yeah?
But-
Well, like I said, why can't you? I mean, there are different ways to do it, but it's just that is a very common way to express numbers when we do proofs. All right, an interesting one that came up, which was the sum of 2 squares, I believe, is always divisible by 4. I think that was. So, prove that the sum of the squares of any, and that's important. I do this one quite early. Any 2 odd numbers is always a multiple of 2, but never a multiple of 4. Okay. So we'll do it together because I can sense what's going to happen. So first of all, let's set up our statement, which is we need the sum of squares of any 2 odd numbers. So my first
2n
odd
plus
number,
1.
so 2n plus 1, I've got where n is an integer. You can just write, by the way, n is an integer. That's fine as well. And we are going to square that. and we are going to add another odd number, what would you do? What would you say?
2n plus 3.
2n plus 3 would make sense. There's a problem with that, though.
Not any.
Good. That is one, by the way, Will, that it is accepted to some extent in the mark scheme, but you wouldn't get full marks.
So like
You just use a different.
You will
letter.
get the same final conclusion, though.
Would you like to make B?
Okay, so this
different
is where you would have to use, to get full marks, a different letter. So 2m
oh,
plus
2n.
1,
Oh, yeah.
or a and b, or whatever. This, where m is a different integer, and we can say n is not equal. No, we can't. We're not saying that. So it doesn't say the sum of n. It doesn't say different. So we're not going to say that n is not equal to m. They're just integers. All right?
So that ought to be squared.
And that has to be squared as well. Now, if we did 2n plus 1 and 2n plus 3, you are proving that two consecutive ones are, and you will get similar result, but you won't get the full-on
Yeah.
correct one. And I like this one. I'm doing this with you now because I think with my upper sixth, this was one that bypassed them a little bit. The first time they did it, and they all put n and so on, right? So to be clear, because they are potentially different odd numbers, they're not necessarily consecutive, we have to do that. Right, so now we are going to use deductive reasoning, hence proof by deduction, that it's a multiple of 2. Let's do that first. How would you approach that? What would you do? Expand it. Okay. So if we expand that, we're going to get 4n squared
Let's do it.
plus
Do it.
4n
Oh, yeah, sorry.
plus 1 plus 4m squared plus 4m plus 1.
Looks good.
Yeah, makes sense.
Oh,
And now we're going to get 4n squared plus 4n plus 4m squared plus 4m plus 2.
Take
What
n
is it?
out of the bracket.
Well, we can. Well, if you take
Take what
2
out
out of it.
I'd say, oh, we take 4 out of the bracket.
Because we can't take an n, but we do it at that little bit, or an m,
Two out of the
but we
bracket,
want
yeah.
to take 2 out of the bracket. So if we want to show that it's a multiple of 2, right? So if we can take 2 out and factorize it, we're all good. So that gives me 2n squared plus,
Oh, but it can be multiple of 4 because you can't take 4 out.
Take the 2 out.
Yeah, because it would be 2 over 4.
plus 1.
Or B 2 or 5.
Okay. It has, remember, a factor of 2. So is a multiple of 2. And then I guess there are a couple of ways you could answer this question. You could go back and try and divide it through by 4 and show that the 2 doesn't divide by 4. You could say that the remainder doesn't divide by 2 because of the 1, but you will need to write another statement, okay, that says there is no further factor of 2 or there is no factor of 4. Hence, there is no, it is never divisible by 4. Okay? QED, if you want. Right. So I'll let you finish off however you think for that. But you can see how there's some formality to, a little bit of formality to the proof.
You have to put QED up every time.
No, I said the QED thing, that's not in a mark scheme. That's, it's just a nice way to show the end. So what I would say is for a couple of you, if there's a proof question, take an extra moment to write things out neatly, clearly, with structure. Practice where you're going to put things. I always put my little information over here. Other people put it, but it needs to be there. So those are important aspects. I don't know whether you want to add that in your notes, that these things are important. Because I'm using a different software, I don't have my little stamps anymore of exclamation marks. So, all right. Does it make sense? Deductive proof now? Easy enough?
Yeah.
Generally? Right. It's in their paper as well. So I probably shouldn't give you this because this is going to be your mock at some point.
No, so
but
roll for it.
yeah, you probably will. Actually, no, it won't, because this year's paper will become your mock, probably, won't it?
I'll write it down.
You'll write it down. You'll memorize.
So is that the 2024 hit?
Yes.
I really need
Right, so we are now going to look at a different type of proof. We're going to look at one that you're going to love, which is proof by counter example. Now it's easy, this particular question. It's only worth 1 mark, but a lot of my upper sixth didn't get the 1 mark for one particular reason. And this question is, and I'm going to, so you can see that there's some similarity to the structure of the question. If you ever watch, I do like the YouTube channel Veritasium. I can recommend watching that if you like. He talks quite often about historical mathematicians and what they did. And that part of their job, or their main job, was to prove things, work things out, develop some, but offer a proof. And then it was everyone else's job to disprove it.
Yeah.
Proof has to cover everything, right? If I'm proving something correct, if I'm proving something wrong, all I have to do is find one example,
Yeah.
and it disproves it. So a lot of my upper sixth students went, well, that's fine. 2 times 3 equals 6.
Didn't put 2 and 3 at all.
Nope. Axioms. 2 is a prime number. We accept. We know that. 3 is a prime number. We accept that. Okay. 2 times 3, that's the product, is equal to 6.
So
6 is not odd.
No, so I'll do
And you need a proof of that.
I know 6.
No, so this is the thing. It is as simple. They all wrote that. I think only a couple use different prime numbers, but you could have done any problem. Give me some others.
And that's right.
70.
They give you a mark.
19.
No. So can you do? So basically, 2 is the prime number you have to use, right? 2 times
It's
any other
anything.
prime number. Some people go, oh, but 1 times 7, 1's not prime, so that throw that out. 3 times 7, that's odd. That works.
So can we just say 2 times anything?
so- No, you can just offer one counter example. There's just one thing missing.
QED.
No, close.
What?
Thus,
6 is an even number,
Most if you explain it.
therefore disproving the statement. It's simple as that. That's all we need to write. But in a proof, we have to show that we are understanding. Because you could write 2 times 3 equals 6, and you could have moved on because you don't know whether 6 is odd or even. Who's to know? Alright? You have provided a counterexample, but the important thing, is to make that statement that says, well, 6 is the counterexample, like 6 is even, all right? It is not odd, therefore disproving the statement. Okay? There's 2 types of proof right there. I do want to go through a couple of bits. We're rattling through quite quickly, but we'll give perhaps Simon a bit. But there are a few symbols that we should look at as well. Okay. and we'll discuss these out because these symbols will get used in proofs. All right. So these symbols are an arrow. Okay. If we say PQ, what does this mean?
Oh, I see. P can turn into Q, but Q can
Okay,
turn into
P implies Q, which basically means if P is true, Q is going to be true.
Is that definite? P is true, Q is definitely true.
Well, it's that implication. Like if it's this system where, like, if I've made a statement, understand this is part of writing a proof. So I can say that, if I get 6, 6 can be written as 2 times 3. That implies that it's even, or something like that. Bit of a dodgy example, but we're basically saying because this one thing is true, that implies that the other thing is true as well. Okay. If I did it the other way round, Q implies P.
and then equal.
And then the final one is that one.
Go either way.
So this is an interesting one because it says P is equivalent to Q, or Q is true if and only if P is true. Now I'll give you a couple of examples again that came up in this paper. It seems to be a lot of this sort of section in this paper. Okay, which is, in the exam, you had to fill in a box, all right, using these symbols. So what symbol would you write for P being x squared equals 3x and Q being x equals 3?
Beautiful. Is it equivalent to?
So what
No,
would
you
that?
need- No, because you need this times x and 3 by x to get P. So Q implies P.
What do you think, guys? Anyone else?
Or can you do both ways?
No. Q implies.
So
P implies Q, sorry.
basically what we're saying is, right, if x squared equals 3, does that imply that x is equal to 3?
Oh,
No.
Mm.
Because X can be 3 for any equation, but
Well, let's not go too
no,
broad.
surely it does, because
If
x
x
equals
is
3,
3,
9 equals 3
is
times 3.
x squared equals 3x?
Yeah.
Okay.
yeah.
So x being in 3 does imply that this is true. If Q is that, P is true.
Yeah.
All right. If P is that, is Q that? Does it work both ways? No.
No, x cubed can't be 6. So 2 cubed is 4. 4 doesn't plus 6.
What?
Plus 2.
Yeah.
What's cubed? Where's the cubed?
That's, if it was 2, let's say,
P implies Q.
then it's not true. It's in all cases.
No, but what I'm saying is, okay, if x is 3, If x is 3, plug that in, this is true.
Yeah.
True, in that direction.
Yeah.
But the
If
other
that is that, if that's true, does that mean x is definitely 3? Why not?
Because if it was,
Yeah, it does.
I mean, what other
There are
number
others,
could you put in for x? To
If, remember, what you're giving me is an example of something where that's not true. So you're sticking with it. That being not true makes that not true as well.
Oh, -3.
-3, that's not true.
If it's minus, yeah.
no, because 9
No,
is
that'd be
equal
9, that's -9, that's not true.
so it's,
So basically, it's true this way, definitely. This being true makes that true. It's not going to work on the video, but back looks like it's true as well, yeah?
Yeah.
Unless we can find a number where it's not true.
Yeah, do you just
0.
0.
Okay, so basically, we have a situation where it's true that way, but it's not necessarily true the other way. Does that make sense to you?
yeah.
All right. So we're saying if x is 3, there's no ambiguity there, then x squared equals 3x is going to be true. Yes, absolutely fine. That's true. But going back, if I solve x squared is 3x, I do get x equals 3, but I also can have x equals 0. Right? Quadratics have 2 solutions. You should have thought that, right? Therefore, the implication is not going the other way. Okay. What about if x is greater than 4, x cubed is greater than 64?
X. Cubed. Oh, well. It's 4 cubed.
So if I pick a number bigger than 4,
900.
will this be true?
Yeah.
Yeah. No way it's not going to be true, right?
Yeah.
So the arrow definitely works that way. If I solve x cubed is greater than 64, will I always get a number that's greater than 4 if I look at it the other way?
So you got 4.
Okay?
I know that, so.
Yeah.
Yeah?
Yeah.
Therefore, this one, both ways. So when you're writing proofs, this is what you're going to be using these symbols. Need to kind of use them appropriately, or probably more importantly, understand when you're reading mark schemes and things. I've seen lots of answers with proofs and stuff where people don't use these symbols, they use words. That's fine. You know, I used therefore this is true, that kind of thing. Instead of writing therefore I can say, well, I would use one of these arrows instead, right? Just to speed things up. And the final one, and I guess we can call the lesson it. We've done 28 minutes of talking. That always highlights it to me.
Are you cutting your videos?
Pardon?
No.
Are you cutting them?
Pure
I,
raw
no, I
footage.
don't bother.
Raw.
It's just unedited raw
Ooh,
footage.
that's tough.
If x degrees is equal to 45, tangent of x is equal to 1.
It's 9.
Okay, so if I put 45 in, the tangent of 45
Is 1.
is 1.
Yeah.
But-
So. that
Definitely
implies-
that way.
Yeah, but it
that
can be
works.
like.
Turning-
Okay, so that's what you're saying. Tan of x
Also,
is 1
different
as
kinds
how
of-
many solutions? An infinite. So the arrow does not go back the other way.
Cool.
Alright. So we can use those symbols to show what's what meaning we have. Like I said, you can also just use words as well if you prefer, but if they give you a proof, for instance, in a question and say spot a mistake in a proof, I don't know, I've not seen one of those yet, but it might do. In fact, it wouldn't surprise me if at some point they start give you a question and test what those symbols mean. Well, actually, they have those scripts, but it's in that last year's paper, so you do need to know what they mean, whether you use them in a proof or not. Okay.